All right, we've been talking about magnetic circuits and really the concept of magnetic circuits. It's such a cool idea, such a cool concept. Anyway, I've got an example here. We've got this magnetic material, it looks maybe iron. It's actually, it's given in the problem, silicon steel. So we've got silicon steel here, and it's like this block, and we've got some coils wrapped around it carrying current I, and we've got all the lengths that are given in centimeters, and we've got a gap there, an air gap, and we're trying to find the flux, or we're given the flux density in the left leg right here is 6/10 of a Tesla, and we're going to find the current in the loop, 1300 turn coil required to get that 6/10 of a Tesla flux density. So let's get started. And really, I mean, the reason this is so cool is because we can set up a circuit, right? And we can use our circuit analysis. And so first of all, I'll point out that the flux through the left leg, which is the flux through the entire material, actually, is this thing here, B times S1. And so why is that? Well, B is the flux density. We know that the coils produce a flux density that is on the axis of the coils, which happens to be parallel to S1, the surface area vector S1. And so when you do B dot ds, since they're in parallel, all you get is B times S. And so that is the flux. And I guess I'll draw the circuit right now. So we've got this kind of equivalent circuit now. We've got the magnetic potential that's due to I and the coils, and then we've got the reluctance of the steel. So I'll make that script R. And then we've got the reluctance of the air gap. Right? Isn't that's such a cool thing? So I'll just write script R gap, and steel like that. So here's our circuit. And so when I say that the flux through the left leg is the same as the flux through the entire thing, what I mean is, there's a series, current, if you will, or a series flux. All right. So we've got that flux. We've got the number of Tesla is 0.6 through the left leg, which is the entire thing, or actually the left leg, and then times S1, which we've got is 5 square centimeters. So that gives us the flux through the left leg, which is through the entire magnetic circuit. All right. Again, that's because B and S1 are in parallel. Okay, so what about the reluctance of the gap? What about the reluctance? Well, we showed that the reluctance of the gap is L, the length of the gap, over mu S2, right? So the length of the gap is given as 0.5 centimeters, and mu is mu 0 in this case because it's air, and S2 would be the surface area, the cross-sectional area of the gap, which is the same as the cross-sectional area here, which is S2, 3 square centimeters. So the reluctance of the gap is given by this thing here, and we have all this. This should be mu 0. So we have all of that, and we can calculate that. And we do have the flux. We can calculate the flux as well. All right, so now let's talk about that. Let's label the potentials here. So this would be the potential, magnetic potential across the steel, right? And this would be the magnetic potential across the gap, VM gap. All right. Okay, so let's be a little bit more clear then. So we can say the VM gap. So now this is the cool part. So now we think of our circuit analysis. So how do I get the voltage across a resistor? I take the current through, multiply by the resistance. So how do I get the magnetic potential across this reluctance? I take the flux through, multiply by the reluctance. Right? So we have all of that. So we've got B times L over let's see, B times L times S1 over mu 0 times S2. So that's, again, that's the magnetic potential across the gap. Now, if you go back to our lecture video on silicon steel, there was that plot where we showed the magnetization of silicon steel, where this was B and this was H, and we had something that looked like this, right? If you go back to that plot, you'll see that a B of 0.6 Weber, or excuse me, Tesla, corresponds to 100 amps per meter. Okay, so from that plot we know that the magnitude of H is 100 amps per meter. That's good. So now we can get the magnetic potential of the steel. Okay, being that H is always parallel to L, we can say, all right, well, what's the length around the steel? Well, the length around the steel is L1, right? And then plus 2L2, because there's L2 this way, and then there's L2 this way. So that's the length around the steel, and then times H, and that gives us the magnetic potential of the steel. And so we have all of that stuff there. So the total magnetic potential then, right, and here's the circuit analysis part, right, Kirchhoff's voltage law, the total magnetic potential is the sum of those two magnetic potentials, the one of the gap plus the one of the steel, like that. We have all of this. So this is the gap again was BL S1 over mu 0 S2, and then of the steel was 100 amps per meter times L1 plus 2L2, like that. And we also showed in the lecture video that the total magnetic potential, right, which is coming from actually the coils, right, the flux linkage and so forth. This is N coils times I, right, the current through each coil. Okay, so now we want that current. We've got the number of turns, so I just divide by N and I've got the current. So I do that. So let's just be concrete here. BL S1 divided by N mu 0 S2 plus 100 L1 plus 2L2 divided by N, and I plug in everything, and I take care of getting everything into meters. So, 8 centimeters is 8 times 10 to the minus 2, but I also need to be careful about the surface area. The area, this is in square centimeters, so that's 10 to the minus 4 meters, square meters, 10 to the minus 4, right? 10 to the minus 2 times 10 to the minus 2, because it's squared. So I take care of that, and I plug in everything, and I get 3.09 amps up to 3 significant digits.